Okay, so it's already 4:05, so let's start. I am Bhargav. I'm a PhD student in IISc, and every week on Saturdays from 4 to 5, I would be taking week problem solving sessions for this course. So let me share my screen and then we can start. I just think someone wants to. Okay, yeah. So let me. So can you see my screen?
Yes, visible.
Okay, yeah.
Yes.
Yeah, so if you have any questions or doubts during the session, feel free to interrupt me. Just unmute yourself and ask the question, because I will be sharing my screen and so I won't be able to see you if you just raise your hand in Google Meet. Okay. Yeah.
Yeah, cool.
So
Yeah.
can you see my laser pointer?
Yes, visible.
Okay. Yeah. Thank you. Okay. So let's start. So before we start solving some problems, we'll just quickly recall what we have learned in this week. Okay. So the first thing we learned was uh, the definition of of the complexity class P. So can someone tell me what P is? Hello.
Yeah, so it's a class of the problems which can be solved by the deterministic Turing machine or by the deterministic algorithms in the polynomial time.
Exactly. So yeah, it's a class of languages or decision problems. Both languages and decision problems are equivalent, that can be accepted or solved by polynomial time deterministic Turing machines. Okay. The next thing that we saw was the class NP, which is the class of languages or decision problems that can be accepted by polynomial type non-deterministic Turing machines. So this is one definition of NP. You would have also seen an alternative definition of NP. So can someone tell me what that definition is?
So yeah, so that was the union of the n time n raised to the power k, wherein I
Right.
mean,
Yeah, that okay. That is also one definition. I had another in mind. The one
so the other definition was that the collection of the problems which are polytime verifiable, problems which can be verified in the, if I mean, if you give me the solution, then I can
right.
verify the solution in the polynomial time.
Yes, exactly. So the alternate definition is NP is a class of languages that can be verified by polynomial type deterministic Turing machines. So even though we might not be able to solve problems in NP efficiently, at least we don't know how to do that till now, we at least know how to verify a solution efficiently. Okay. Yeah. And so obviously it's P is in NP. That's clear, right? Because if you can solve something, you can also verify it efficiently.
So I have a doubt
Okay.
here regarding the use of the terms accepted. So
Okay.
accepted by the polynomial time deterministic Turing
Hmm.
machine. Does it mean decided by the polynomial time deterministic Turing machine? So wherever the term accepted is
Right.
written here, can we replace it by the term decided, because the acceptance also gives a feeling of the recognition kind of the thing,
Okay. Yeah. I think.
and
Yeah.
which
So
is.
I think you can use accepted, recognized, decided almost interchangeably.
But in case of the recognition, we do not the answer of no. There is always a possibility of, I mean, for the Turing machine to enter into the infinite loop if the string is not the part of
Right.
the
No. But so
language. So in
okay.
that
So
way,
if I were to replace accepted by recognized, what would it be? The class of languages that can be recognized by polynomial time deterministic Turing machines, right? So once I
yes,
say that a Turing machine is polynomial time, it has to halt, right?
yes, correct, right,
Right. So basically, both in P and NP, I have some condition on running time, right? So that forces me to halt.
right,
Right.
acceptable,
Yeah.
right.
Okay. So those were the classes P and NP. Now you would have also learned about polynomial time reductions. So language A is said to be polynomial time reducible to a language B if there exists a polynomial time computable function f from sigma star to sigma star. Here sigma is the set of alphabets, so sigma star is the set of all strings, such that x is in A if and only if f of x is in B. And this is denoted by A polynomial time reduces to B. So I hope everyone is clear with this definition of polynomial time reductions, okay? Because there are some
Sir,
questions
can you
based on
explain what
this.
is polynomial time?
Oh, polynomial time computable function?
Yes, sir.
Okay, so I say that a function f is polynomial time computable if there exists a deterministic Turing machine which on input x outputs f of x in polynomial time. So for example,
Sir, in the second, note that, sir, in the second point, you said a less than and something, this symbol I can't read. I don't know about it. I asked about this.
can you repeat the
Less than
question?
equal to p.
Right.
In the second point, denoted by a less than equal to the p. What is the use of this p and what?
Oh, so this notation less than equals to p means a is reducible to b in polynomial time. So p stands for polynomial. This is just a notation. It doesn't actually mean that a is less than b. It's just a notation.
Can you give an example for this, sir? If you have any?
Okay, so example for a reduction. So in
Yes,
the
sir. Any function which can be reducible.
okay, so in the lectures you would have seen that 3-sat reduces to clique or 3-sat reduces to independent set.
Yes, sir.
Yes. So in this case, 3-sat would be your A, and clique or independent set would be your B. And
Okay, sir. Thank you, sir.
if you want an explicit example of a reduction, I think towards the end there are about 10 problems, and I think the ninth or the 10th problem has a reduction. Okay, so we'll see one reduction today as well. Okay, so
So, thank you, sir.
yeah.
Yes, so in this slide, in the previous slide, but in the lectures are also mentioned that not only for all the x which are the elements of A,
Right.
but for those x also which are not the element of
Okay,
A.
right, exactly. Yeah, so
So
over there he might have used this sign. So this is a double imply sign, right?
yes,
In the lecture, what he might have done is the following. Let me see if I can write. So in the lecture, he might have done the following. X in A implies f of x in B, and
mhm,
x not in A
mhm,
implies f of x not, not in B. Did you do
right,
something like, okay, right. So
yes,
these two combined mean just this, right? That x is in A if and only if f of x is in B.
correct,
Because what
correct.
does this
Yeah,
first statement say? It says that if x is in A, then f of x is in B. This says
right,
that if x is not in A, then f of x is not in B. So this together
correct.
just mean this, right?
Yes, yes,
Yeah.
yes.
Yeah. So then you would have also seen what NP-complete languages and NP-complete problems are. So can you tell me what the NP-complete languages or problems are?
So if the language is the element of itself is the element of NP,
Right.
and all the problems which are there in the NP can be reduced into this problem, then the problem is an element of the NP. So problem is NP complete.
Right. Yeah. So as I said, so these are sort of the hardest problems in NP. Let me get back my pointer. Yeah. And so as I said, a language A in NP is said to be NP complete if all languages in NP are polynomial time reducible to A. And uh, observe that to show that a language A in NP is NP complete, it is sufficient to show that there exists an NP complete language B, so that B reduces to A in polynomial time. So is this last point clear? Because we would use this in one of the problems.
Yes, so I was having a doubt here,
Okay.
and I wrote this thing on the forum also that it is true that NP complete are the hardest problem in NP.
Hmm.
What about the NP hard problems?
Okay.
So
Yeah. Okay. So
so is it appropriate to say that NP hard problems are even harder than NP complete problem, because in that case the problem itself need not to be the element of NP.
Okay, so it is certainly true that there exist NP hard problems which are harder than all problems in NP. But it need not be true for all NP hard problems. So what you can say is some NP hard problems are harder than problems in NP are harder than problems which are NP complete, but not all. Because every NP complete problem is also an NP hard problem, right?
Because all NP complete problems are NP hard problems. Uh, yeah,
Right,
true.
right. So what? Okay, so I can give you an example of an NP hard problem which is harder than every problem in NP. Have you heard of the
Mhm.
halting problem?
But then that problem is undecidable.
Right,
So
but it is also NP hard because you can reduce every problem in NP to that problem.
yes,
So it's
so
NP hard but not NP complete.
yes, so can we take A? Can you write A as an element of the NPR? Probably it would be easy for me to
Okay,
uh, explain my doubt
okay.
that if A
So
is the element of NP
okay,
hard,
so let me
then
write
A
about
need not to be the
A
element of NP.
in NP hard
Yes, so then A
if
need not be the element of NP.
for all B in NP,
Yeah.
uh, B reduces to A. How do I erase that? Yeah. B reduces to A in polynomial time. Okay, so this is a definition of NP hard languages.
Yes. So certainly this A cannot be the element of P. So either it is the element
Okay,
of
it
NP.
cannot be an element of P provided P not equals NP. We still,
Yes,
it is
yes.
believed that P not equals NP, but we still don't have a proof.
Yes. So we
Right,
do not.
right,
And now, so certainly this A is more difficult, or at least as difficult as a NP class problem is.
right. So you, I don't think
So,
we can say that A is harder than every every problem in NP,
so
but
then
we
what
can
could be the class
certainly
of
say that A is at least as hard as every problem in NP.
right. So
Right.
then what would be the potential or the possible class of A? If it is not NP, neither it is P, nor it is NP. So
Okay.
what could be what is the name of the class to which this problem A
Oh, it's
belongs?
the name of the class is NP hard, right?
Yes, but then only A. So A is if A is not the element of NP,
Hmm.
and all the problems which are there in NP can be reduced to this problem.
Right.
So then, what could be the complexity class of the problem A then?
Okay, so there are many classes beyond P and NP,
Yes.
and you would see some of these classes, I think, in the next week or the next to next week.
Okay.
Yeah. And okay, so you've already seen one such class. Okay, actually, you've already seen two such classes if you have done theory of computation. First class is a class of decidable problems.
Mhm.
It is beyond NP, right? Because I can
Uh,
always cook up a problem which is not in NP, but is decidable.
I could not hear you.
Oh,
Yeah.
sorry.
What did you say?
Yeah. So what I said is, if you have seen theory of computation, you've already seen two complexity classes which are
Mhm.
beyond NPs. Okay.
Mhm.
One is the class of recursive languages or decidable problems,
Right.
and another is the class of recursively enumerable problems or languages.
Mhm.
Right. So these two
Mhm.
are beyond NP,
Are beyond NP.
as in
Okay.
they contain NP.
Mhm.
Right. And in fact, what you would see in the next few weeks is that there is an infinite chain of classes which contain NP. Each one each one potentially harder than the previous one. Yeah.
Okay.
So just remember this question. We can maybe discuss it when you actually see that in the class.
Sure.
Okay. Yeah.
Okay. Yeah.
Okay. Okay. Let's start with the problems. So the first problem is the following. Out of the following choices, select all the choices that are definitely false. Okay. So that are known to be false. The options are P equals NP. Oh, I should change to your laser pointer. Sorry. The options are P equals NP. P is strictly contained in NP. So this notation, if you don't know, means that P is a strict subset of NP. So P is a subset of NP but not NP. The third option is P and NP are intersecting sets, but neither of them is a subset of the other. And the fourth option is P and NP are disjoint sets. So can you tell me which of these options are definitely false? Multiple options can be false. Okay, so let's go over the options one by one. Is it okay? Do we know that P equals NP is false?
No, we don't know.
Right, we don't know a proof for this, so we cannot say that this option is definitely false. Okay. What about P being a strict subset of NP? Do we know that this is true?
Yes, this is true.
No. Over here it's a strict subset, not just a subset.
Okay.
So
we
right,
do not.
Right, because what P being a strict subset of NP would mean is that P not equals to NP, which is a big open problem. We don't know don't know an answer to that, right?
Yes.
Okay. So what about the third option? P and NP are intersecting sets, but neither of them is a subset of the other. Is this true or false?
This is false.
Right.
False.
Why?
Certainly false. Because I mean, P is a subset of
Right.
NP. It contained. I mean,
Right.
they're in the NP.
Right.
Uh,
So this part of the statement is false, right? Okay. And the fourth option is P and NP are disjoint sets. Is this true?
no, this is false.
Right, because P is a subset of NP, and so therefore P and NP cannot be disjoint, right? So the answer is C and D. And yeah, we know that P is an NP, but we don't know whether P equals to NP or P or not equals to NP. This is a big open problem. Okay, so let's move on to the. So if everyone is okay with this, we will move on to the next question.
Yes, sir.
Okay. So the next problem is the following. Consider the problem of determining if two given integers are relatively prime. Do you know what does it mean when I say that A and B are relatively prime? Just a second. Someone wants to join the meeting. Did someone put something in the chat?
Yes, sir. Mr. Parashnath Chaudhary put something.
Okay. So you want me to explain the first problem in the diagram? Okay. Let me go back. Okay, I have some space over here. Okay, so which options do you want me to explain? So we already know this, right? This is NP. And this is P. Oh, okay. So but we do not know if this smaller circle is the same as a larger circle or not. Okay. So we do not know if P equals to NP. This is an open problem. This thing is equivalent to P not equals to NP. Yeah. Okay, yeah. So the second option is equivalent to P not equals to NP, which is also an open problem. So proving that P is either equal to NP or not equal to NP are open problems. So we cannot say for sure if A and B are false. Okay. However, let's look at the third option. P and NP are intersecting sets, which is true because P is contained in NP, and so P and NP do intersect. But neither of them is a subset of the other. This is not true, right? Because we know that P is a subset of NP. Is this okay? Okay. And the fourth option says that P and NP are disjoint sets. This is also not true because P is contained in NP. Okay. So the third and the fourth options are false. Is this fine?
Okay, sir, I understood.
Yeah. So yeah, then we can move on to the next problem. So the next problem is, consider the problem of determining if two given integers are relatively prime or not. So before we go to the options, do you know what relatively prime integers mean? Or should I explain it?
Co-prime numbers.
Right. So their greatest common divisor is just 1. Okay. Right. So the question is this problem in P and in NP, in P but not in NP, in NP but not in P, and neither in P nor in NP. So can someone tell me which of the following is correct, or should we go over these option by option?
So I think that the answer is A.
Okay.
Because computing GCD, I mean GCD can be computed in the polynomial time, and since it is there in P, so it is there in NP as well.
Right. Yeah. So that's the answer. It's in P, and therefore it is also in NP because P is contained in NP. And the reason is, so as I said, two numbers A and B are relatively prime if and only if their greatest common divisor or GCD is 1. And the GCD of A and B can be computed in polynomial time using Euclid's algorithm. Are you guys familiar with Euclid's algorithm, or do you not know about it? So if you don't know about it, you can, I think, yeah, this is a fairly standard algorithm. You can look it up on Wikipedia, and if we have time towards the end of the session, I can also explain this algorithm using an example. Okay.
Yeah, I forgot its complexity because Euclid was very much polynomial, but somehow its complexity is skipped from memory.
Yeah, so its complexity is, let me write it. Yes, its complexity is, okay, so suppose that A is greater than equals to B, okay. Then the complexity is log 2 base B.
Yes.
So, right, so its complexity is logarithmic in B. Okay, sorry, it's not this, it's order this. Okay, yeah, order is always there. So if I wanted to give you A and B, I would require 2 log B bits, right?
Yes, yes.
Right. So the algorithm runs in time polynomial not in A and B, but in the bit complexities. So in the input size. Okay, so it's completely polynomial time. Right. Okay, so let's move on to the next problem. Okay, yeah, so this is a mouthful, so let's go over it slowly. Where is my pointer? Yeah. So consider the following algorithm to decide if a given integer n, the integer is given in a binary form, is prime or not. Okay, this is a very standard algorithm. I think all of you would have coded this up in C or C++. So the algorithm is as follows. Starting from I is equal to 2, we try out dividing n by each integer I till we reach I equals to square root n. So for I in 2 to square root n, divide n by I. Okay, if we find that n is divisible for some such I, then we output that n is not prime, that is n is composite. Otherwise we output that n is prime. So is the algorithm clear?
Yes, sir.
Yeah. So the question is so choose between these 4 options, whichever is correct. The algorithm correctly decides that n is prime and is a polynomial time algorithm. The second option is the algorithm correctly decides that n is prime, but it is not a polynomial time algorithm. The algorithm is incorrect but runs in polynomial time, and the algorithm is incorrect and does not run in polynomial time. So can anyone if you tell me or guess which of the 4 is correct?
Sir, A.
Okay, yeah, so you are saying that the algorithm correctly decides that n is prime and it is a polynomial time algorithm. Okay.
I think it is B.
Okay.
Because checking primeness is recent. I mean, is proved by this from Professor
AKS.
Manindra Agrawal recently. Yeah, AKS.
Right.
That's it.
Yeah. Okay, so the answer is B. Okay, so first of all, does everyone agree with me that the algorithm correctly decides that n is prime? Is that okay with everyone?
Sir.
I couldn't hear you. Can you say it out a little louder?
Yes, sir.
Okay, yeah.
Yes.
Okay, so the only thing that we have to worry about now is seeing whether this algorithm is polynomial time or not. Okay. Okay, so let's see. Okay, so what is the worst case running time of this algorithm? It's ordered square root n. Okay, is this fine? The reason is the following. In the worst case, n would be prime. So I would have to divide n by all numbers from I equals to 2 to I equals to square root n. So I would have to divide n order square root n times. So the worst case running complexity is order square root n. Okay. Now you might be tempted to say that, okay, The algorithm runs in time order square root n, so it's polynomial because square root n is polynomial in n, right? However, so when we say that an algorithm is polynomial, algorithm is a polynomial time algorithm, what do we mean? We mean that it runs in time polynomial in the input size, right? So now,
Yes, sir.
so how were we given n as an input? We were given n in its binary representation, right? Over here we were
Yes,
given
sir.
n in its binary representation, right? So how many bits do you require to write n in its binary representation? We saw this in the previous question, right? It's small n, which is less than or equals to ceiling of log n, right, base 2. So the input size is order log n, not n. Okay, is this fine?
Didn't get it, sir.
Yes.
Can you say it again? Your voice.
I didn't got it, sir.
Okay, so we were given n as a binary number, right? And if I want to write n as a binary number, how many bits do I need?
Yes, sir.
Can you say that again? Hello?
I am not able to calculate it, sir.
Okay,
Please
yeah.
tell me.
Okay, so let's try a few examples, okay? Yeah, okay. So we have a number n, right? Let's say n is equal to 5. How many bits do I need? 1, 0, 1. This is 5, right?
Yes, sir.
Now what is log 5? This is 3, right? Sorry, ceiling.
Yes,
Okay,
sir.
right. Then okay, so then let's try with 10. So 10 is 1, 0, 1, 0, right? And what is
Okay, sir. It's perfectly understood now.
right? Okay,
Beautiful.
yeah. So the input size is order log n. That is fine, right? Now let us see what the running time is as a function of the input time. So we want to now write the running time as a function of small n, not capital N. Okay. So the running time is roughly square root n. I am ignoring the order over here for the sake of simplicity. So the running time is roughly square root n, which is n to the 1 over 2. Okay. Now I can write this capital N as 2 to the log n. Is everyone fine with this? Writing n as 2 to the log n? This is fairly standard.
Yes, sir.
Yeah. Okay, so n to the 1 over 2 is 2 to the log n to the half, which is just 2 to the log n over 2. Okay. Now, as we saw over here, log n is order n, or n is order log n, right? So I can write this quantity as 2 to the order n over 2, right? So the running time of our algorithm, which is order square root n, is 2 to the order n over 2, which is not polynomial in n, but it is exponential in small n, right? So the algorithm is not polynomial time in small n, which is input size. So is this okay with
Yes.
everyone?
So
Yes, sir.
this also relates to that how do we determine the size of the problem? Say whenever we compute the complexity of the
Right.
quicksort, then we used to say that okay, the average complexity is of the order of n log n,
Right.
and there we do not mention that what I mean. There we compute the n as the size of the problem as the, but we do not mention it as the number of the bits occupied, etc.
Right. So generally, almost in every problem, we give input as binary numbers. Okay.
Mm-hmm.
So what would happen in quicksort is, suppose I gave you a list of n numbers, and let's say the largest number is capital B. Okay.
Mm-hmm.
And let me define this small b. I'm using a laser pointer. So let me define this quantity b is equal to log capital B. Okay. Then what would be the size of the input? It would be at most n times b.
Mm-hmm.
And if you recall quicksort, all the operations we were doing were just comparison, right?
Mm-hmm.
So I can compare two B bit numbers using just order B time, right? Order B operations.
Mm-hmm.
So if you want to write down the uh, time complexity of quick sort,
Mm-hmm.
it would be something like this: n times b times log n,
Mm-hmm.
right? But generally we ignore b because it is almost always understood that you are given input in binary, and in most cases this is fine. Most cases ignoring b is fine.
Mm. Right,
Yeah.
right.
But yeah, there are cases like this when it gets you into trouble. Okay. Yeah.
Yes.
Okay. So yeah, as someone mentioned, this problem of deciding whether a number is prime or not is actually known to be in P because of the wonderful result by Manindra Agrawal, Nitin Saxena, and Neeraj Kayal in 2002. So if you are interested, you can look it up on Wikipedia or search AKS primality test. Okay. So let's move on to the next problem. And let me switch to the laser pointer as well. Yeah. So which one of the following serves as a witness or certificate to the to the fact that 3 colorable is in NP? Okay, so the options are minimum spanning tree, a proper 3 coloring, a BFS tree, or a minimum cut of the graph. So can anyone guess the answer?
So it's B.
Okay, yeah. Okay, so the answer is B, and the reason is the following. A proper 3 coloring exists if and only if a graph is 3 colorable, right? Okay, that is just trivial, right?
Okay, sir.
Yeah, so all we have to do is, suppose I give you a 3 coloring. Okay, all I have to do is check whether it's valid or not, right? But that is easy. Why? Because I give you a 3 coloring, you color the graph using that coloring, and for every node, look at the colors of all of its neighbors. They should be different than its own color, right? This can be easily done in polynomial time.
So do you have access to the forum of this class as well? Do you see the questions posted there in the forum of this class?
Yes, right, yeah.
Do you have access to the forum of this
Yes,
class?
yes.
Okay, all right. Yeah. So I have today only I have posted one
Okay,
query there. That I mean, so probably I did not properly phrase the question. So my query was that what if we make a modification in the problem formulation that uh, uh, the the violation won't be that two adjacent vertices. Violation is that not two adjacent vertices are having the same color, but I mean there could be a distance of one edge in between two vertices. So
okay.
if we modify this problem in that way, so do you have idea that whether such a formulation exists or not, wherein I mean, we give a different notion of the violation of the constraint,
Okay,
different meaning to the violation of the
okay,
constraint.
so if I understand correctly, what you are saying is uh, it's a stricter version that, okay, let me draw it. So is this what you are saying? So suppose we have these 3 vertices.
Yeah,
This is colored with color 1,
yeah.
this is colored with color 1, and there is an edge like this.
That is not allowed. That is not allowed because now we are having a difference of one edge or the two edges in between,
Right.
say, yeah. So, and similarly, we can think of many more edges in between, and this variation of this coloring problem.
Okay, so suppose we had this situation. I'm just trying to understand your question properly. 1 and 3. Even this is not allowed, right?
This is not allowed because
Right. So
there
the
is not.
distance should be at least 3. That is what you are saying.
Yeah.
Okay, I haven't I think seen this problem, but I think, okay, so I might be wrong, but I think this is also this is also NP hard and NP complete, because what you can do is you can always create another graph where this is also an edge, right? Creating such a graph is easy, right?
Yes.
And then the problem that you proposed becomes 3 coloring for that graph, right?
So I mean, such a triple can always be constructed, or then the job would be to identify the possible triples existing in the given graph.
Hmm.
So yeah, so that itself is a problem.
Right.
That is a problem.
Yeah, so okay, this is just one way to do it. I mean, there might be some other simpler ways.
Yeah.
Yeah, so I think this might be NP complete, but I'm not sure. I haven't
Yes.
seen this problem. Yeah.
So I'll have to work on it, and
Yeah.
then we can see it in the next session.
Right.
Sir,
Oh
can
wait,
I
wait, wait.
ask
This is
you
directly NP
doubts?
complete, right? Because no, wait, no, 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 no. That's not true. Yeah, I would think. I would have to think about this. Yeah. Okay.
Yes.
Someone else was asking a question.
Sir, I have doubts
Yeah.
from the assignment 0 related to the complexity questions.
Okay. Yeah. Just
Can
a
I
second.
ask
I think
them?
someone wants to join. Yeah. Yeah. Hello.
Okay. Hello.
Yes.
Sir, do you have access to the week 0 assignment?
Okay. So is that assignment graded? It's not graded, right?
Non-graded. It's not
Okay.
graded.
Yeah. Then we can discuss it. Okay. Yeah. So, what's the question?
Okay. The second question: which of the following is or are true?
Hmm.
Sir, how is the second option true?
So,
The fourth option. How is it true?
okay. So, can you tell the options as well? Because right now I haven't opened the assignment.
S- Uh, wait a minute. Sir, it is written that log n is a subset of O log O n.
Oh, this order login is a subset of order n. Is this what it's written?
Yes, sir.
Okay. Yeah.
Sir,
So,
order log n is not written. Only log n is written.
okay. So, if it's login, then I think it should be in order n. Not a, is this symbol used or this symbol used?
Yes, the second one. Second one, sir.
Okay. 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 So there is a. So if you recall the definition of ON, it's technically a class, right?
Yes, sir.
Right. So okay, this is the correct way of writing it, but we generally write it like this. So because if you recall, what is the definition of ON? Uh, yeah. So F is equal to ON if there exists N0. Uh, if there exists N0 comma C such that for all n greater than equals to n0, f of n is less than equals to c times n, right? So On is a class of such f's, right? And log n is certainly satisfies this property, right?
Okay, sir.
Yeah. So is this fine?
So would it
Yes,
be
sir.
would it be little O or big O?
Big O is also fine. Little o is also fine, right? Little o is stricter than big O. So okay, little o of n is
Probably little O will make much sense rather than big O here, because then big O and won't be an asymptotically tight bound of the
right.
log.
Right, but it is also it's not asymptotically right, but it's the statement is still true, right? Because small o of n is contained in big O of n,
Uh,
right?
yeah,
Yeah, so
this
you are right. A tighter bound would have been small o of n, but capital O of n is also fine.
okay, okay.
Yeah. Okay, so let's move on to the next problem. Okay, so yeah, so the next problem is what is the number of satisfying assignments of this Boolean formula? Okay, the formula is x1 and x1 or x2 complement and x2 or x3 complement and x4 or x5 complement, x4 or x5, right? Yeah. So does anyone want to guess or should we work this out?
So at least uh, we require I mean the x1 has to be true, and then x2 has to be
Oh, wait,
true,
wait. I think there is a.
and then x4 has to be true. So at
Oh, okay.
least,
So okay, there is a typo in this slide. This should be x1 bar. So x1 complement or.
okay,
Right.
okay.
Yeah.
You can continue with the solution. It is difficult to guess.
Okay. Yeah. So okay. So this is the formula. So okay, when is the formula true? It is true if and only if every clause is individually true, right? Because there is an and in between. So is this fine? This first statement?
Yes, sir. Yes, yes.
Yeah. Okay. So let's try make. So what is the simplest clause over here? It's this x1 complement, right? So let's try making this true. So this is true if and only if x1 is 0. Okay, so here I am using the convention that 0 is false and 1 is true. Okay, just for the sake of simplicity. So we need x1 to be 0. Okay, so let's fix x1 is equal to 0. Now let's look at the second clause. What does the second clause become once we fix x1? It becomes 0 or x2 complement, which is just x2 complement, right? So then the second clause becomes x2 complement, which is true if and only if x2 is 0. So let's also fix x2 is equal to 0. Now what does the third clause become? It becomes x0 or x3 complement, which is this x3 complement. So the third clause is only true if x3 is 0. So let's also fix that x3 is 0. So we have fixed x1, fixed x2, fixed x3. Now we are only left with x4 and x5. Okay, so to satisfy this clause x4 or x5, so far we have satisfied these three clauses. Now we are only left with this clause and these two variables. So there are three ways to satisfy this, right? 0 1, 1 0 and 1 1. So our satisfying assignment would look something like this: 0 0 0 0 1, 0 0 0 1 0, 0 0 0 1 1. So these are the only three satisfying assignments. Does everyone agree with me?
Yes, yes.
Yeah.
Yes, sir.
Okay. So let's move on to the next problem. By the way, one more question. Yeah, you were asking something?
Yes, so what about this problem that counting the number of the satisfying assignments? So is this also NP complete? Considering that the set is NP complete, so
Oh,
yeah.
wait. Okay, so this problem, that was what I was going to ask you. Is this problem over here NP complete?
Here,
Yeah. Okay, not over here, but something like this, where every clause is at most two literals. Is that problem NP complete or not?
no. This won't be NP complete
Right.
because
There has to be,
yeah.
three. So the three set is NP complete, right? There must be a
Yeah.
clause with three literals. Otherwise, this is easy.
Yes, because in order to have something meaningful, even in the chemical equations, right, we should have two elements in the left of the equation and one in the right. Then only something meaningful will occur. If we have only two elements, so then it is merely a transformation and not a chemical reaction kind of a thing. So in order to observe some dynamics, at least three variables are required. So therefore, the two set is in P and this three set is. So sir mentioned this thing explicitly in the
Right.
lecture that yeah, three set is the minimum requirement to
Right.
be.
Yes. So yeah. So if so a formula like this, so this would not be NP complete because we have only, this is only two set. Okay. So now your question was, is counting the number of assignments of three set NP complete or not, right? Was that your question?
Yes, yes,
Okay.
yes.
First of all, my claim is this problem is not even NP. Can you tell me why?
Which problem?
The problem that you mentioned, counting the number of assignments of a 3 CNF formula.
Uh, okay, this is not even there in the
NP.
NP.
Yeah. Okay, so what is the definition of NP?
Yeah, probably because the even the number of the even the to verify that whether the given solution, in fact, I mean, given whether the given assignment indeed is a solution or not, but then we can always do it. And then yes, so I think that it is very much. I mean, it is more or less same as solving the satisfiability problem?
No, no, no,
Because
no, no.
once we
You
have the
can
assignment
no
and once we can
in
verify,
satisfiability problem you only need to check if one assignment exists or not, right? Here you have to count the number of assignments, which is much harder, right? Because
yes,
just
yes,
even if I give you one assignment, there is no guarantee that another assignment does not exist or does exist, right?
correct, correct.
Okay.
So probably this would be same as a complement of the satisfiability kind of
No,
thing.
no, no.
Maybe.
It is not even that. So okay, there is one very simple reason why this is not in NP. What is the definition of
Mhm.
NP? It is a class of languages or decision problems, right?
Mhm.
So the way you have stated it, the way you have stated the problem is, I give you a formula phi. Tell me the number of its satisfying assignments, right? That is not a decision problem, right? It's a counting problem.
Yes.
So it cannot be in NP, right?
Yeah. True. True.
However, this problem is NP hard. Why?
Mhm.
Because if you could count the number of satisfying assignments, you could
Mhm.
also also decide whether the formula is satisfiable or not. Why? Count the number of assignments. If it is 0, the formula is not satisfiable. If it is at least 1, the formula is satisfiable, right?
Yes.
So
Yes. Yes.
this is an example of a problem which is not in NP but NP hard,
Yeah.
right? And in fact, if you are interested in such counting problems, towards the
Mhm.
very end of the course, you would see a
Mhm.
class which is a class of counting problems.
Okay.
Yeah,
And what's the name of the complexity class?
it's called sharp P.
P sharp. P sharp.
Yeah,
Yeah.
okay,
All right.
yeah. Okay, so let's. So if everyone is okay with this, let's move on to the next problem. Okay,
There
so
was a question in the chat. Someone asked the question.
please don't write in chat because I can't see the chat because I'm presenting. Okay, I didn't. Oh, so you understood it now? Okay, yeah. Yep. Instead of writing in the chat, please try to unmute yourself and ask the question because I can't see the chat while I'm presenting the screen. Okay. So let's move on to the next problem.
I have a small query here.
Right.
Regarding the nature of the problem, that this problem is not a decision class problem, so all the optimization problems can be viewed as the decision class problems and vice versa.
No, all optimization problems are decision problems, right? Okay, we because in optimization problem you have to uh, find a number, right? A solution. Over here you have to just decide whether it's there or not.
Yes, so optimization is same as deciding something beyond a limit.
Yes, okay, you are right. There is a way of reducing every optimization problem to a decision problem.
And vice versa.
Yes, yeah.
And vice but then the counting problem is not, can't be viewed as a decision class problem, assuming that if I put a threshold or if I set a
Yes,
threshold that,
that you can do.
okay,
Yeah,
okay, but then also this problem is NP hard, is it?
right. Yeah, because okay, so I don't want to get into this because all of this you would see all of this come when you look at sharp P.
Mhm.
Yeah,
Okay, okay, all
yeah,
right, yeah. So we can discuss it
yeah,
later then.
right.
Yeah, thank
Okay, so let's move on to the next problem. So here we are given uh, two problems, the clique problem and the intercept problem. You have probably seen these two in the class. So the clique problem is the following: you are given a graph and a number k, and this tuple is in the set clique if G is an undirected graph and has a clique of size greater than or equal to k. The second problem is the intercept problem, and you are given a tuple G and k, and G is an undirected, and this tuple is an intercept if G is an undirected graph and has an independent set of size greater than or equals to k. Wait, yeah, this should be. Wait, no, I've messed up this. So clique has to be. Okay, I think it's fine. Yeah. So the largest independent set and min. Wait, G is an undirected graph and has an independent set of size at least k, and this should be, yeah, okay, that's fine.
you. It should be n minus k, I think. somewhere in the second, if the size of, if you're seeking for the size of the click greater than k, then the size of the independent set would be greater than or equals to
Yeah,
n
yeah,
minus.
yeah. That is what I was thinking. But I mean, it's fine. We are not looking at the same graph, right?
Yes. Okay.
Yeah.
Okay. In that case,
Yeah, I mean, okay. And anyways, okay. So k can okay. So these are two different definitions, right? K can be different. Okay. Yeah. So here, so we have to select the correct option. Yeah, someone wants to enter. Sorry. Yeah. So we have to select the correct option. There are four options. Clique is polynomial time reducible to int set. So sorry, neither clique is polynomial time reducible to int set, nor is independent set polynomial time reducible to clique. The second option is clique is polynomial time reducible to int set, but int set is not polynomial time reducible to clique. The third option is int set is polynomial time reducible to clique, but clique is not polynomial time reducible to int set. And clique, the fourth option is clique is polynomial time reducible to int set, and int set is also polynomial time reducible to clique. So would anyone of you would like to guess the answer? Okay, so if there are no guesses, let me tell you the answer
then
is, yeah,
it is D. It is
okay,
D.
yeah, the answer is D, and the reason is the following. So you would have seen in the class that both clique and int set are in NP. So has this been covered in the class?
No, no. Sir explained the about the click and the set and the click.
Okay,
But then getting the independent set is like computing the click of the inverse graph kind of
right.
in that.
Okay, yeah. So okay, so these both languages are in NP, and both of these are also NP complete. Okay, so these two are known facts. Okay, is this fine? Okay,
Yes,
so
yes.
okay, so now what do we know? We know that clique is in NP and independent set is NP complete. Then by the definition of NP completeness, it must be that clique reduces to independent set in polynomial time. Is this fine?
Yeah. So is this reduction one-way function or uh, can it be? I mean, it is not necessary that the reduction is a two-way function kind of a
Right. Yeah.
thing.
So we would come to that question later. Okay. So yeah, I think that is either the next question or the next question.
Yeah.
Yeah. So but for now, clique is in NP and independent set is NP complete. Therefore, by the definition of NP completeness, clique reduces to independent set. Is this statement fine? Here we are not even talking about what the reduction is. We are just saying that a reduction exists. Is this
Yeah.
clear? Why is this true?
Yes, yes, because click means the largest number of the.
Okay, no. You are thinking of a concrete reduction. Okay. What I am saying is the following. Clique is in NP and
Mhm.
independent set is NP complete. Now, what is the definition of NP completeness?
So all those problems which are there in NP are
Right,
bound to reduce to that problem.
right.
So
So, by the very
because of
definition of
yeah,
NP completeness, this is true.
yeah.
Okay, yeah. And similarly, independent set is also in NP
Mhm.
and clique is NP complete.
Correct,
So,
correct.
independent set should also reduce to clique.
Yes,
Right.
yes.
This is one way to do it. Another way to do it would be what you were saying, do an explicit reduction.
Mhm.
Right. Okay, so if this is fine, we'll move on to the next problem. Okay, so this is the thing you were asking, right?
Yes. So this is not true.
Okay, yeah. So the question is, if A is polynomial time reducible to B, then is B also polynomial time reducible to A? Yeah, and this is false. The reason is the following. What does it mean to say that A is polynomial time reducible to B? It means that there exists a polynomial time computable function f such that x is in A if and only if f of x is in B. Now you might be tempted to say the following. Okay, x is in A if and only if f of x is in B. So let me do the following. This is the same as saying this, right? F inverse of x is in A if and only if x is in B. And so F inverse X is a reduction from B to A. You might be tempted to say this, right? However, the problem is the following. An inverse of a function only exists if the function is a bijection, right? If it's a 1 onto function. However, in this definition over here, we aren't told that F is a bijection, right? So F inverse need not exist. So you can't say this thing, the thing that I've written. Is this clear?
So I have a query here.
Yeah.
So is there a repository available, or I mean some database available, database kind of the thing
Right.
available from where we come to know that okay, I mean this problem is having these characteristics, and because of these characteristics, this problem is likely to be reduced by this problem.
Okay, so if you're talking about reductions between NP complete problems, then
Like say how someone would come to know that okay, this is the satisfiability problem which is the nearest one to which can be reduced to the click problem and not the, I mean,
okay,
because
so
movie reduction itself is a very difficult task.
yeah, so I think I think 2 or 3 years ago I knew of such a website where basically almost every known NP complete problem was listed, and
Mhm.
it was also listed from where the reduction happened. Yeah, but right now I've forgotten that website.
Yeah, so I'm also looking for
Yeah.
such a resource. And moreover, my second query is that does there exist a mechanism through which we can show that a reduction will definitely exist or will definitely not
Oh, I don't
exist?
think there exists such a mechanism, because even today you would see
Hmm.
research papers coming up where some problem would be proved to be NP hard or NP complete.
Yeah, okay.
Yeah. So there is no like royal way to a reduction. You have to just try a bunch of problems and figure out which works.
And, and just out
Yeah.
of curiosity, what about the undecidability of the such a problem that that yeah, so this problem can never be solved?
Okay. So yeah, there are problems even today whose undecidability is not clear to us.
Okay, okay,
Yeah.
okay.
Okay. So yeah. So
Right.
yeah. So yeah. So over here we show that F is not a bijection, and so F inverse need not exist. Let's just quickly see this with a diagram. Okay. So let us. So over here the green ovals are sigma star, the set of all strings. Uh, every string above this orange line is in A, and every string below is in A bar, and same over here, right? Now we have an F which reduces, which basically maps this part to this part and this part to this part, right? However, this can be the situation, right? That F maps this part to a very small subset of this part and this part to a very small subset of this part. So for any string over here, there is no, F does not give you anything over here, right? That is why you cannot say that F would also give you some sort of reduction in this direction. Is this fine?
Yes,
Yeah.
yes.
So this is basically a pictorial way of saying that F need not be a bijection, and so F inverse need not exist. Okay, yeah. So the next problem is the following. Suppose a language A can be reduced to a language B in time O n to the 4, and B can be reduced to another language C in time also O n to the 4, right? Then A can be reduced to C in time O n to the k. Find what is the value of this k. So is the question clear?
Yes, question is
Yeah.
clear.
So does anyone want to guess what k is?
So yeah, so the smallest value of k I think could be equals to 4 only, say.
Yes, so that is, it is very tempting to say the following. I can
Hmm.
reduce A to B in order n to the 4 time.
Mhm.
After I have done that, I would reduce B to C in order n to the 4 time. So the total time would be order n to the 4 plus order n to the 4 is equal to order n to the 4, right? This is very tempting.
But then at least some time is required to, I don't know, not sure.
Okay, so yeah, there is one, so there is one problem which is reasoning. So let's see what is the problem. Okay, So suppose that f is a function that reduces a to b and g is the function that reduces b to c. Then g of f or g composed with f is a function that reduces a to c. Why? X is in a if and only if f of x is in b, because f reduces a to b. And similarly, f of x is in b if and only if g of f of x is in c. So this basically proves that g of f is a function that reduces a to c. And because of this reason, we only need to compute the running time of g of f. Is this clear?
Yes, yes.
Okay. So now let's compute the running time of g of f. Let us suppose we are given a string x and its length is n. Okay. Then the string y is equal to f of x can be computed in time order n to the 4, because f runs in time order n to the 4. Okay. Now, okay, yeah. Okay, there is a typo here. This is y. So now suppose that the length of y that we have computed over here is m. Okay. Then g of y is equal to g of f of x can be computed in time order m to the 4. So what is the total computation time of g of f of x? First you compute y and then you compute g of y. G of y is your answer, right? So the time required to compute y is n to the 4, order n to the 4, and the time required to compute g of y is order m to the 4. So the total time is order m to the 4 plus n to the 4. Okay. Is this okay?
Yes, and but there has to be some limit over the value of m also.
Right,
because
that is what we are going to do. So now what we need to do is we need to find how large m can be, right? Because suppose m is n square, then your answer would be n to the 8, right? Okay, so does everyone agree with me that if we are able to show that m is upper bounded by something, we are done? Is that fine?
Yes.
Okay. Now let's see what m can be. Does anyone want to guess?
So since you are transforming this m, I mean you are getting this value of m through a polynomial time function.
Right. In fact, an order n to the 4 time function.
Yes. So at the most it can be say of the okay. So this is being computed in of the order of n raised to the power k. So the value of m could be of the order of n raised to the power 4k. 4k.
No, k is what we are supposed to find, right?
4 raised to the power say t, because you are transforming this thing, a string of the length n, through a polynomial time algorithm.
Not just a polynomial time algorithm, an order n to the 4 time algorithm. You are very close.
So this is polynomial time only? No.
I can do better than polynomial time, because what I know is that f runs in time order n to the 4. Okay.
Yes.
Yes. Let me tell you what it is. Okay. So because f can be computed in time order n to the 4, the maximum possible value of n is order n to the 4. Why? Because in order n to the 4, you cannot write anything more than that, right?
Yes.
You have to at least write down m. Because what should f do? F should output y, right? So f has to at least write down y.
Yes.
And because f has only order n to the 4 time to run in, even if at every second it writes one bit down or one symbol down, it can only write at most order n to the 4 symbols, right?
Yes.
So its output, the size of its output can be at most order n to the 4, right? Right. So m is n to the 4. So you were saying it's polynomial time. You were using the same logic, right? F is polynomial time, so its output cannot be super polynomial, right? Here we are just making it tighter. We are saying that f runs in time t, so its output cannot be larger than t. The size of its output cannot be larger than t.
Yes.
Right. So hence g of f of x can be computed in time n to the 4 plus n to the 4. which is just order n to the 16, right? Because we can ignore this. This dominates. So k is 16. So is everyone okay with this?
Yeah, this is very interesting problem.
Yeah. So saying that A reduces to B in order n to the 4 and B reduces to C in order n to the 4, so A must reduce to C in order n to the 4 is very tempting.
Yes,
Yeah, I
yes.
agree with that. So let's look at the next problem. So suppose there is a language L in NP that is not NP complete, and L is also not equals to the empty set, and L is not also the set of all strings. Okay. So in which of the following statements can we infer from this? The options are P equals to NP, P is a strict subset of NP, P is not equals to NP, and NP is contained in P. So multiple options can be true. So does anyone want to guess, or should we see the solution? Okay, so if no one wants to guess, we can look at the solution. Okay, so the answers are these two: P not contained in NP and P not equals to NP. Okay. So is the question clear to everyone?
This question is not that clear.
Okay.
I mean, language of the question is not clear.
Okay, so what this is saying is the following. Somehow someone told you that there exists a language in NP which is not NP complete. Okay. And also that this language is not the empty set or this set. So this is information you are given. You are supposed to assume that this is true. Okay. Someone told you this. Then they are asking if this statement is true. If this statement is true, then which of the following is true? So what can you infer from this statement? Okay, mind you, right now we do not know whether this statement is true or not. We do have no proof of this statement. But what the question is asking is, suppose this statement were true, then what can you say? So is the question clear now?
So I mean, what is the impact we are making over L by making these two statements that L is not equals to phi and
Right.
L is not equals to the entire world?
Yeah, so these two, we would see why these two are important in the solution or proof of this statement.
Okay.
Yeah, so these two are very crucial.
Mm-hmm.
Okay, so if the question is clear and if you, just remember these two options, then we can move on to the proof or solution of this problem. Okay. So let us first observe that options A and D are equivalent. So what was option A? P equals to NP. What was option D? NP is contained in P. I am claiming that these two are equivalent. Can you tell me why?
So if P is not contained in NP, then it will not be equal to NP either.
Oh, no. Right now I think you are talking about B and C. Right now I am talking about A and D. So what I am saying is A and D are equivalent. Okay, so let's see why they are equivalent. Okay, so if P equals to NP, then NP has to be a subset of P, right? Because every set is a subset of itself, right? So this implies that A implies D. Similarly, we know that P is contained in NP. This is known, right? So if D were true and NP is also contained in P, then P and NP are contained in each other. They have to be the same, right?
Yes.
So options A and D are equivalent. Okay. The next thing we'll do is we'll show that options B and C are also equivalent. Then we are essentially left with just two options, right? A and B. Okay. So let's see why. So option B says that P is a strict subset of NP. But this would mean that P not equals to NP, right?
Yes.
So which means that B implies C. Now we know that P is contained in NP. So if there is a typo. So if P were not equals to NP, then P must be a strict subset of NP. Do you agree with this?
Yes.
Right. So C also implies B.
Mm-hmm.
So B and C are equivalent. What we have done is we have simplified this question. So we had 4 options. Now we have boiled it down to just 2 options. P is equal to P not equals to. Okay, I have messed up the option. We have just boiled it down to 2 options. P equals to NP and P not equals to NP. Basically, we have made the question simpler so far. So far, we haven't proved anything. Okay. Now let us show that this would imply P not equals NP. Okay, which is what we are going to do next. Okay. So what I am claiming now is the following: if P is equal to NP, then every language in NP which is not empty or the universal set is NP complete. So is the statement of the claim clear?
Empty NP. Okay, yes.
Okay.
Yes.
So now we'll see how to prove this. Okay. Okay. So let us fix a language A in NP, which is neither empty set nor universal set, but is okay. So let us fix an A in NP which is neither of these two. Okay. And what we will show is that this language is NP complete. Okay. That would prove the claim, right? Because the claim is saying that
If P is equal to NP, then it is NP complete. I mean, there is no issue, because if P is equal to NP,
right.
so I mean, what's the purpose of giving a proof of it? If it is P is equal to NP, neither if it is phi and not the entire world, then it is all the problems can be reduced into this problem. Straightforward.
Exactly. So okay. So what we are going to do now is we are going to say how the reduction happens.
Okay.
So okay. Since you have said that this is we can do this, can you tell me how would you reduce this? How would you reduce every problem in P or NP, which are the same, to A?
Because if I am reducing the problem A into the problem B, then the problem B is at least as hard as the problem A is.
Right.
So if P is equal to NP, then if A is not phi or lean closure of sigma, so then it means that all the problems can be reduced into this. So this problem would be at least as hard.
Right. So what I'm asking is, here you are making a claim, right? Every problem in P can be reduced to A. I'm asking you, how would you do this reduction? So you would have to show that there exists a function f satisfying that x is in B double implies f of x is in A, right?
Yes.
So I'm asking you, how would you show that such a function exists? That is exactly what we are going to do in this proof.
Okay.
Okay, so is the purpose of the proof clear now?
Mm-hmm.
I agree with you. Intuitively it feels simple. That's right. Yeah. If P equals NP, then you should be able to do this reduction, right? But now we'll see how to do this formally. Okay. Okay, and here, so you also asked this question, right? Why is this condition important? A not being zero, empty set or the universal set, right? So here is where it comes in handy. So we are going to fix a y1 in A and a y2 not in A. Now observe that such y1 and y2 only exist because A satisfies this condition.
Yes.
Because if A were empty, y1 won't exist, and A were the universal set, y2 won't exist. So
true.
These y1 and y2 we can only pick because of this condition. Okay. Now we are going to do a very stupid reduction. It's very trivial. Okay. So here's what we are going to do. For any x in sigma star, we would check if x is in B. So now this can be done in time polynomial in the size of x, because B is in NP and NP is P, right?
Yes.
So if x is in B, what we'll do is we'll set f of x is equal to y1. And if x is not in B, we'll set f of x is equal to y2.
True.
Now, because of the way we have defined f, it is clear that x is in B if and only if f of x is in, this should be A. This is clear, right? Because of the way we have defined f, right? Because what are we doing? Whenever x is in B, f of x is equal to y1 and y1 is in A, right? So whenever x is in B, f of x is equal to y1 over here and y is in A. Similarly, whenever x is not in B, f of x is equal to y2 over here and y2 is not in B. So this statement is true. Do you agree with me?
Yes, yes.
Also, f can be computed in time polynomial in size of x, right? Because what are we doing? We are just checking if x is in B or not, which can be done in polynomial time because x is in P. Sorry, B is in P.
Right.
So we have shown that there exists a function satisfying this, which can be computed in time polynomial in x, size of x. So what we have shown is that B reduces to A in polynomial time. Okay, this is what we wanted to prove, right?
Yes.
Yeah, and this is true for every B in NP. I haven't imposed any condition on B right now, right? So what we have shown is that every language in B reduces to A. Therefore, A has to be NP complete, right?
Yes.
Right. So far what we have shown is that if P equals this claim, if P equals to NP, then every A in NP which is not like this must be NP complete. But recall what does the question say? The question says that there exists a language in NP which is not NP complete, which is not empty set, and which is not universal set. So basically this violates this claim, right? But what was the assumption of this claim? P equals to NP, right?
Yes.
So the claim is violated, therefore the assumption must be false, right?
Yes.
So if what I'm saying is if P were NP, then such a language L must not exist, right? That is what we have shown, right? But the question says that such a language must exist, such a language exists, which means that P cannot be equals to NP. The answer is, so that means that P cannot be equals to NP, right? So the answer is C. But we've also shown that C and B are the same, right? So the answer are C and B. So is this fine?
Yes, yes.
Yeah. So okay, let's look at the last problem, and here we see an explicit reduction. Okay, so someone asked this question, right? Can you give an example of a reduction? Yeah. So now let's see an explicit reduction. Yeah. Okay. So we are given two languages, short path and long path. Okay. Short path is the language of tuples G, S, T and K, such that G is an undirected graph, K is greater than or equals to 0, and there is a path from S to T of length at most K. Long path is the same language, but this at most changes to at least. And we have four options. Both short path and long path are in P. Short path is in P, but long path is not known to be in P. Long path is in P, but short path is not known to be in P, and neither short path nor long path are known to be in P. So we are supposed to pick the correct option, and would anyone like to guess what the answer is?
So is this B?
Short path is in P, but long path is not known to be in P. Yeah, that's the answer. Okay, so let's look at why this is true. Okay, so let's first look at short path. So we know that there exists Dijkstra's algorithm, and using that we can find the shortest path within S and T in G. This we can do in polynomial time, right?
Yes.
Yes. And so once we have found out the shortest path, we can also check its length, right? In polynomial time.
Yes.
Right, so we can determine if the length of the shortest path is at most K in polynomial time. Therefore, short path is in P. Is this fine?
Yes, yes.
Okay. Now let's look at long path. Okay. Now what we'll do is the following. We'll show that long path is NP hard.
It is not there even in NP, because even the verification would be all that more difficult.
Okay, so we can't say that it is not in NP, right? All we can say is that we don't know whether it is NP, right? In NP, right? Because right, you are right. If you were to do it in the trivial way, by giving all the paths and checking, then you are right. It's difficult to do it, right? But I mean, there always exists a possibility that there is a very smart certificate that works out, right? You can't rule that out, right?
But if the smart verification exists, so this will lead to altogether a different complexity class, because for the meaning for a class for a problem to be in NP, the verification should be done in the polynomial time.
Right.
That's
No,
it.
right.
This is the only
So what I'm saying is there can exist a smart certificate X for this problem. The certificate that you have in mind is the following. Look at all the paths between S and T and then check the longest path, right?
But the number of paths would be
Right. No, but what I'm saying is
exponentially large
right.
number of the paths.
Yeah, so what I'm saying is that is just one certificate, right? That is just one candidate certificate, right? Right, that is the most obvious, I agree with you. But that is just one candidate certificate, right? You cannot rule out the fact that there exists another certificate which is much smaller, designed in a very smart way. Right now, remember, okay, right now we don't know whether such a certificate exists or not. That is true. But we can't say it does not exist, right? Yeah, that's the point I'm making.
Yes,
Okay,
right, correct.
So what we'll do is, that is why I've written NP hard, not NP complete. So we will show that long path is NP hard. Okay. And since we don't know whether P is equal to NP or not, this would imply that we do not know whether long path is in P or not, right? So do you agree with me that if we just show this, then we would have shown that long path is not known to be in P?
Could not hear your question.
Okay, yeah.
Can you repeat the
So
question?
my question was, do you agree with me that if we show that long path is NP hard, then we would have shown that it is not known whether long path is in P or not? That is what we want to show, right? Yeah, okay. So what we'll do is we'll reduce some NP complete problem to long path. Okay. The problem that we are going to use is the Hamiltonian path problem. So let's recall what a Hamiltonian path is. A Hamiltonian path in a graph G is equal to V comma E is a path that visits every vertex exactly once. Okay. So is the definition of a Hamiltonian path clear?
Yes.
Okay. And the NP complete problem that we are going to use is hem path, defined as G. So that G is an undirected graph and G is a Hamiltonian path. Okay. And this is a very standard NP complete problem. You might or might not have seen this in the class, but this is very standard NP complete problem. Okay. And what we'll do is we will show that this problem reduces to long path. And this would imply that long path is NP hard. Okay. So now let's do this reduction. Okay. So given an instance of G of the Hamiltonian path problem, what do we want to do? We want to create, and so to avoid confusion, let me call this G prime. We want to reduce the Hamiltonian path problem to the long path problem. Okay. So what do we want to do? We want to create an instance of the long path problem given an instance of the Hamiltonian path problem. Okay. And we'll do this as follows. So now our reduction starts. So first of all, we will construct a graph G prime from G as follows. So over here, this red circle represents all the vertices of G. Okay. What we'll do is we'll add two extra vertices, call them S and T, and connect this vertex S to every vertex in G and this vertex T to every vertex in G. This is how we would construct G prime. So are you clear with the construction of G prime?
No. This construction is not clear. So how are we? So S and T are the given vertices.
No. Okay, so right now there are no given vertices, right? Because we are starting off with the Hamiltonian path problem.
Mm-hmm.
and we want to construct instead of the long path problem, right?
Mm-hmm.
So right now the only given thing is a graph G,
Correct.
and we are supposed to find whether there exists a Hamiltonian path in it or not, right?
Mm-hmm.
So what I am doing is I am constructing a new graph G prime for the long path problem.
And how are we constructing it? I mean, how are we are we augmenting the given graph G with
Yes,
the two additional vertices or
right,
what?
right. So we have G. We would add two new vertices to it, S and T,
Mm-hmm.
and then connect both of them with every vertex in G.
Yes.
Okay, so is the construction okay now?
Yes, construction is okay.
Okay.
Under the condition that the Hamiltonian path exists, then such a construction would be possible,
No,
otherwise not
this construction
possible.
would be possible even if the Hamiltonian path doesn't exist, right?
So if the Hamiltonian path doesn't exist, then how would you traverse from S to every other vertex
Okay,
within
no,
the
no.
graph?
So right now, forget about the paths. The
Mhm.
graph G prime you can still create if the Hamiltonian path exists or not, right?
Yes,
Yeah,
yes.
you are right. There might not be a path from S to T and all of that,
Mhm.
but G prime you can construct in polynomial time.
Mhm.
So,
That's true.
right. So this G prime, okay, so immediately gives us this instance G prime S T K that we are interested in. How? If G has n vertices, we'll set K to be n plus 1. Okay. This we can also do in polynomial time. So from G, we can create G prime S comma T comma K in polynomial time. Is this fine? So far we have just given a construction. We haven't argued anything about whether if G has Hamiltonian path, then G prime has a long path or something like that. Okay. So
So what K here is?
K is n plus 1. N is the number of vertices in G.
And this K is the number of the vertices in the G prime or what?
No, it's 1 less than the number of vertices in G prime. We would see why this value of K is important later. Okay.
Okay, okay, all right, yeah.
Right now I'm just asking if is this construction clear and are you convinced that this is polynomial time?
Yes.
Okay. So now we have given a construction. We have given a, so what we have basically done is the following. We have given a polynomial time commutable function f.
Still it is not clear that how can we construct this G prime in the polynomial time.
Okay.
Even if we make all the assumptions that we are using this G as a black box and we are not sure that
No, no,
whether
no.
the
We are not using G as a black box. We have G is given to us in the Hamiltonian path problem, right?
Mhm.
So let's say G has n vertices. It is very easy to add an extra vertex S and add an edge from S to every vertex of G in polynomial time, right? You can do this in order n time, right?
Yes, that we can do.
Similarly, you can do it for T.
Correct.
And K is just counting how many vertices are there in G and adding 1 to it, right?
Mhm. I mean, from the S, we are not traversing within
No,
the
no, no,
graph.
okay, forget about traversing and everything right now. Right now, we have just constructed G and G, this G prime from G.
Correct, correct.
This construction is fine. This construction is in polynomial time, right?
Yes, yes.
Yeah, so we would worry about the traversal from now on, okay?
Mhm.
So right now, up till this point, what we have done is the following. We have come up with a function f, which is polynomial time computable, such that f of g is equal to this tuple g prime s comma t comma k. Okay. Now, what we are going to show is that g is in hem path. I have written it over here. G is in hem path if and only if g prime s t k is in long path. This would complete the reduction, right? Do you agree with me?
Yes.
Okay.
And vice versa. And vice versa.
No, vice versa is not required because this is double implies, right?
Okay. Okay.
Yeah, so vice versa would have been required if I would have used this.
Mhm.
Yeah, because
True.
the vice versa is just this, and this is just a combination of two, right? So let's see. The first claim is the following. It's the first one direction. If G is in Hamilton, if G is in hem path, then G prime S comma T comma K is in long path. Okay. Let's see why this is true. If G is in hem path, then there exists a Hamiltonian path. Let me call this path V1 to Vn. V1, V2 up to Vn. Okay. So is this fine? This is the definition of the Hamiltonian path problem, right?
Yes.
Okay. Now let us find out the length of this path. It is n minus 1.
Yeah.
Oh, by the way, over here by the length of the path I am using the definition, the number of edges. Okay.
Mhm.
So the length of this Hamiltonian path in G is n minus 1. But then notice that the path S, V1, V2 up to Vn, T is a legitimate path from S to T in G prime of length n minus 1 plus 2 is equal to n plus 1, right? This is why K was chosen to be n plus 1.
But yeah, but then even though I understand the region, but then why are we connecting S to all the vertices of the given graph G?
Oh yeah,
A single edge would have been sufficient or would
no,
suffice.
there is a slight problem, right? Suppose you were to connect.
We would not know from that vertex whether a path exists.
Right. So you do not know whether, let's say you connected S to V2, right? Now the Hamiltonian path starting from V2 might not exist.
Yes.
But if you connect it to everything, you are guaranteed that you are going to pick a right vertex, right?
Yes.
Yeah. So that is why you need all connecting to everything business.
Yeah.
Okay. So what this statement says is that this Hamiltonian path would give us a path of length n plus 1 from S to T.
True.
And therefore G prime S, T, K is a long path.
Yes.
Because of this nice choice of K.
Yes.
Right. So we have shown one direction. Now let's show the vice versa. Okay. The vice versa is the second claim. If G prime S, T, K is a long path, then G is an Hamiltonian path. Okay. The proof is as follows. Notice that as G prime has n plus 2 vertices, n vertices of G plus 2 vertices, S and T. The length of the longest path from S to T in G prime is at most n plus 1. It cannot be more than n plus 1, right?
Yes, true.
Right. Okay. Now, suppose that G prime S, T, K is in long path. What does this mean? This means that there exists a path S, V1, V2 up to Vn, T. That is a path of length n plus 1. But the only way to get a path of length n plus 1 is if you visit everything. Right. So are you fine with this statement?
Yes, very much.
Right.
Very much.
So but notice that this path immediately gives us a Hamiltonian path in G. V1 to Vn, right?
Yes. Do we have a unique Hamiltonian path every time for every graph?
No, not necessarily.
Not necessary.
Right. So yeah, you are right. There can be multiple long paths in G prime, right? But any path works for us, right?
So there could be multiple long paths, but then would be having the same value of the length. Is this?
Okay. So when is G prime S, T, K long path? When there exists a path from S to T of length at least K. But you know that every path from S to T must be of length at most K. So the length is less than or equal to K, greater than or equal to K. There is only one number that satisfies both of these conditions. So what I'm saying is the length A is greater than less than equals to K. Length A is greater than equals to K. Therefore A is equal to K, is equal to n plus 1. Right. So there is, because of this very nice choice of K, the length of the long path is unique. Right.
But there could be multiple long paths.
Yes. But we are fine with that. That won't mess with us, right?
Yes.
That would give us different Hamiltonian paths, but we are fine. We just want one Hamiltonian path. Right. So yeah, there's a typo here. So V1 to Vn is a Hamiltonian path in G, and just G is an Ham path. Do you agree with this?
What did you say? I mean, your video got missed.
Hence, V1 to Vn is a Hamiltonian path in G.
Yes.
Thus
True.
G is an Ham path by the very definition of Ham path, right?
Yes.
So what we have shown is that G is an Ham path if and only if G prime is S, T, K is a long path. So we have accomplished this reduction.
Yes.
So we have shown that long path is NP hard, and therefore it's not known to be in P, because we don't know if P is equal to NP.
Yeah, this is very interesting and very intuitive problem, and clarifies the idea of the NP hard as well.
Yeah.
Yes.
Okay, so do you have any question? Otherwise we can end.
No. We'll be having another interaction on next Saturday.
Yes, so throughout this the duration of this course, we would have
Mhm.
such an interaction every Saturday from 4 to 5.
Okay.
Sir,
Yeah.
any another day for interaction or something?
Uh, I think your voice broke. Can you say it again?
Sir, I said, is there any other day fixed for interaction of something? Actually, I have taken another course to machine learning.
Okay.
There, the discussion is going for 4 days.
Oh, okay,
So,
so I think the reason for that is you might have four TAs over there. I am the only TA for this course.
yes,
Which
So
course is that? Which course is that in the machine learning wherein the interaction is held for 4 days?
introduction to machine learning it is.
Okay. Okay.
Sir, another problem is
right.
that in that course too, there is a discussion going on Saturday in the same time slot.
Okay. Yeah, so the thing is we have already given these time slots. So the time slot we can't change the time slots now. But what will happen is the
Uh,
following. We would record these, so we are recording these sessions and then we would upload these to YouTube. And we will share the links with you.
okay, will you share the links personally or
No, no, so I think
Neptune will mail?
we would share it with NPTL, NPTL would share those with you.
Okay, sir.
Yeah.
This is might go
Right.
fine.
So
So fine.
then what you can do is you can attend one of the two sessions. For the other session, you can watch the video, and if you have some doubts, you can ask in the forum because all of us TAs would be there in the forum.
Yes, sir, I'm trying to
Okay.
see.
Yeah.
And sir, another thing, will you share this PPT with us?
Oh, right. So I would, yeah. So I would also have to share this PPT with NPTL, and they will share it with you.
Okay, from where can we download this?
No, no. So what I'm saying is, I would share these links with
Okay,
NPTL. They would
I
send you an
got it.
email or something like that.
Okay, okay,
Yeah.
okay. Thank you, sir.
And anyways, so let's
And
if they don't share something like this before, let's say next Friday, then what you can do is just put this thing in the forum. Say,
and
and I would
okay,
just put the links in the forum.
another thing, sir, just
Right.
a simple doubt. A set of integers
Hmm.
is countable or uncountable?
Well, the set of integers is countable. In fact, that is sort of the definition of roughly a definition of countability. It's
But sir, it goes till infinity.
right. Okay, yeah. So okay. By the way, there are two types of infinity, right? Countable and uncountable.
Okay.
So okay. So what is the definition of a countable set?
Mm, maybe a fixed number of items.
No, 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 no,
Something.
no. That is a finite set, right?
Yes.
So the definition of a countable
I
set.
don't know. Actually, I don't know.
Okay, the definition of a countable set is for the following. Set S is said to be countable if and only if there exists a 1 onto function from the set of integers to S or the set of natural numbers to S.
Okay.
Yeah,
Set of natural numbers.
natural numbers or integers doesn't matter, both are fine.
And sir, what is S in this case?
So S is any set, or what I'm saying is a set S is said to be countable if and only if there exists a 1 onto function from the set of integers or natural numbers to S.
Okay, sir.
Yeah,
Thank you, sir.
yeah. Okay, so if we don't have any other questions, then we can end this session and we can meet next week.
Thank
Thank
you,
you
sir.
so
It
very
Yeah.
was
much.
a very great
Thank
session.
you so very much.
Thank you. Okay, see you. Bye.
Bye.